So in this lecture, we're going to proceed with our formal understanding of some transformation rules regarding tensors, but we're going to focus on the notion of tensor densities. And I've introduced the idea a few times by showing you things that don't transform the way normal tensors transform, and I said, oh, we're going to call these things tensor densities. Well, now we're going to formally define this idea. And I'm going to start with the classical definition. And I'm going to do that for two reasons. One is I've always kind of complained about the classical definition of tensors, and much of these lectures sort of circumvent the classical definition, and the way we do it is we include basis vectors, right? I always talk about dragging around these basis vectors, and the classical definition, of course, the classical definition of nothing, of any of these stuff none of it has basis vectors in the classical sense. And what that generally means is that if I'm talking about a tensor A mu nu A mu nu partial mu tensor product partial nu, this is how we think of it. We think of it as the full, complete structure, but in the classical sense, they only think of it as A mu nu, right? They only think of it as with the components. And that's why they define their tensors as things that transform a certain way. Whereas we understand that A mu nu, we can slap in there an inverse matrix that takes mu to mu prime, and another inverse matrix that takes nu to nu prime, and a matrix, a non-inverse, a straightforward covariant matrix that takes mu prime, or alpha to mu prime, and matrix that takes, say, beta to nu prime. And this whole thing equals 1, so we're not really changing anything. And then we've got alpha and beta like that. And what we basically have done is we now create A mu prime nu prime, right, through contraction here and contraction there, and we create partial mu prime partial nu prime through contraction here and contraction here. And this whole thing, if you looked at that contraction and this contraction, you ultimately end up with identity matrices, right? That's straight matrix multiplication is what's going on there. So the point is, that's how we look at things. We look at things where we're multiplying by 1 all the time when we make a transformation, because we've got to transform this and we've got to transform this. But in the classical world, it's not multiplying by 1, which is kind of an easy thing to understand. In the classical world, you've got to multiply by a matrix that doesn't end up being 1, or a pair of matrices that doesn't end up being 1. So it looks more like a rule of some sort, nu prime nu. So now this thing is some kind of rule, and they lay down that rule, and you have to remember the rule. And this notion here, which motivates the rule, that is taking a tensor in the unprimed frame and multiplying it by 1, that concept they never get to, but we understand that, and so our understanding is, frankly, it's a bit deeper. There is a profound irony here, of course, because once you've done all the work that we've done, and once you've gone through all this process, where now we think in these terms, and we're carrying around these darn basis vectors everywhere we go, right? Once you've done that, you're like, holy crap, do I have to really carry around these basis vectors? And what you do is, once you understand it, then you revert to the classical definition anyway, right? You're not going to do real general relativity problems by dragging these guys around. And we also, in preparation for the fact that ultimately we will abandon these things, we have redundant information, right? We redundantly track the order of indices in the component with the order of indices in the tensor basis. That's too much information, right? That's redundant. This ordering and this ordering, it doesn't have to be that way. We could put any ordering here, and this ordering always tells us what tensor product space we're in. But if we plan to abandon this someday, if we plan to get rid of this, then we better have something that reminds us of what the ordering is. And so what we do is we keep it there. So ironically, we berate the classical presentation, but ultimately we're going to go back to it. And when we start my course in general relativity, I can promise you we're not going to be dragging around the basis vectors all the time. We're going to do everything with the pure component notation alone. So I said all that to say that when we talk about tensor densities, I'm actually going to reverse the process. I'm going to start with the classical definition and then connect it to our definitions that involve dragging around basis vectors. So let's begin. We will start with a classical definition of a tensor density. And I will do this by drawing it this script ET, tensor density. Now that's different from this script ET, right? This script ET was the PQ rank tensor product space, right? That's a whole vector space. I'm looking for just one little object that I'm going to call a tensor density. And I'm going to start with an example of a tensor density that has one contravariant index and one covariant index. And furthermore, I'm going to call this a weight 1 tensor density. So I'm looking for a weight 1 tensor density. And I'm going to draw it with this symbol here. Script E straight T with one contravariant, one covariant index. Understanding I could do this for any level of any rank, so to speak. So I could have 2, 3, 4 covariant and say 2 contravariant. And any possible combination of covariant and contravariant indices will work here. And it could be a tensor density. But I still have to decide what weight it's going to be. And the weight, could be a weight 1, could be a weight 3, could be a weight -2, any integer, including 0 really, right? It just turns out that a weight 0 tensor density just reverts to a straight-up tensor, a regular tensor. So anyway, I'm going to work with this object here. I'm going to call and this will be a rank 1, 1 tensor density of weight, and I have to decide what the weight is. There's no symbol in here to throw down the weight, but I need to know the weight. So I'm going to call it a weight W. You could almost imagine saying, well, I should include the weight. If I'm going to have a symbol for a tensor density and weight's important, I should have a little W for a weight. So maybe I should put that little W there. But let's work through what the definition is and then worry about the symbol, I guess, later. So our definition is going to be tensor density mu nu. And that's the object. Now, the way in the classical system, the way we define these objects is how they transform under a coordinate change. And we already know that if you change the coordinates, say from dx dx mu prime, from dx mu to dx, from the prime to unprime coordinates, right? Where this thing this matrix, I'm going to put lines here to indicate that it's a matrix, right? That thing we're going to call lambda mu to mu prime. And if that's the covariant transformation, it's the thing that's going to take the basis vectors of the underlying vector space V and transform them from the unprime frame to the prime frame. So this is the covariant transformation matrix. And of course it works on the basis vectors, which in this case, since it's a coordinate basis, right? The coordinate basis, I've expressed it as these partial derivatives, and we know that this thing can always be understood in terms of a coordinate change. Any coordinate change can be understood as a linear transformation, and this is the rule, right? So, so now we have to apply this coordinate change will participate in the definition of a tensor density in the classical world. Because remember, in the classical world, they confuse the components of objects with the objects themselves, or they certainly do that for tensors, right? They talk about the tensor as, oh, it is its components, right? They say, oh, there's the tensor. This is a rank. This is a rank 0, 2 tensor, and that is the tensor, right? They don't, not including the basis vector. So we're doing something similar here. This thing is defined by its transformation rule. We're going to find a transformation rule for something we're going to call a tensor density. So to do that, we have to literally write it down as a transformation rule. So I'll put the prime frame there, and then I will put the unprimed frame here. Oops, unprimed frame there. And then I will write down the transformation rule. Well, the first part is actually totally familiar, right? It's going to be the inverse matrix to go to the prime frame for the contravariant matrix. It's going to be the covariant matrix for the covariant index. Oops, new, right? So that's totally normal. If I stop there, this thing would be a regular tensor because it would transform, the indices each transform exactly the way we expect. The difference, though, is that I am now going to, I said it was weight 1, so I'm now going to include a factor of the determinant of lambda to the first power. That's where the weight shows up. That weight shows up right there. It's the first power of the determinant is an additional factor. Remember, this is just a number, right? So it's an additional factor that gets thrown in there that doesn't belong if it was a regular tensor. And that additional factor of the determinant of the covariant transformation matrix makes this a rank 1, 1 tensor density of weight 1. And so the rest of the more general definition would then be something like this. I'll say I1 ... to IK, J1 ... to JK. I guess I'll have to put primes on all of this, equals the determinant of the transformation matrix, that object, let me make it with brackets, raised to the power W, and then there's going to be lambda I1 prime I1 ... lambda IK prime IK multiplied by lambda inverse J1 prime. Wait a minute. Have I got this backwards? Yeah, of course this is backwards, right? These are the contravariant indices need the inverse, right? So I've got to change these guys to their inverse. Let's see, I better just erase the damn thing. I'll just erase it. So this is lambda inverse I prime 1 I1 ... lambda inverse I prime K IK, and then it's lambda j1 prime lambda j, not k. I'll make that, this can be totally different, right? They don't have to have the same k. So I'll make it jq, this has to be prime, jq prime, and then of course it is, let me take this and just shrink it a little bit, sorry. Shrink it and straighten it out. And then I need a t I1 ik j1 jk. Okay, phew. So this is the definition of a tensor density of weight W, and this would be a rank KQ tensor density of weight W, right? Now, it's interesting, there's a little notation out there, or a little verbalization out there that seems to be gaining in popularity. I've seen it very slightly, where if W is less than 0, we call this a tensor capacity. Right, not common usage, but if you go out there, you'll find some usage of this idea of a tensor capacity. But it doesn't really matter, it's just whether or not W is positive or negative. And clearly, if you see if W equals 0, right, if W equals 0, then this thing reduces entirely to the normal tensor transformation rule. So the normal tensors are simply tensor densities of weight 0 in principle, right? So that is the classical definition of a tensor density. And what we found is when we did our analysis of one of the exterior powers, we discovered that it transformed like a tensor density. Specifically, we discovered that a rank 1 tensor density, we discovered this thing pk prime was equal to the determinant of lambda times k prime k pk, right? That was the transformation of the components of this object that we showed that the n-1, an element of the n-1th exterior power could be recast as this guy, where now we're dealing with a rank 1 tensor density of weight 1, obviously. So basically we showed that elements of the n-1th exterior power could be understood as equivalent to these objects that are rank I guess in this case it's rank 1, 0 tensor densities of weight 1, right? That's what we showed at the end of our last lecture. And now what I've shown is the general rule of what types of things are called tensor densities in the classical sense, meaning these objects, this combination of numbers, if it transforms under a coordinate transformation in this way, we call it a KQ tensor density of weight W. So now the question is what the heck are these things, right? How is it that you create this kind of transformation rule? And these collections of numbers, right? We were offended by the notion of tensors just being asserted as a collection of numbers that transform in a specific way. So we should be no less offended in this case. So we want to figure out what is it that these numbers are and why and how can we bring this concept into the fold of our thinking when we want to add basis vectors to everything? Which is another way of saying, are these connected to some sort of base vector space out there? Is there a vector space akin to a tensor product space, right? A tensor product space is a vector space. Is there a vector space out there for which these things have some connection? And the answer, of course, is yes. And what space is that? So before we go there, why don't I just do sort of an example that might shed a little light. So that example is going to be, I'm going to create another brand new object, right? Ultimately, this object will in fact be a tensor density, but I'm going to pretend like it's something completely new. Let's call that object, I'll call it Fancy K. Fancy K, something like that. And it will, Fancy K is some sort of tensor-like object out there, but I'm going to write it down in the following way. In fact, the way I'm going to write it down is it literally will be a tensor with a twist, so to speak. And I'm going to write it down so I'll have, let's say, Fancy K, and I'll give it two indices, mu and nu. And now I'm going to give it a basis. And that basis will be, the first part will be exactly what we expect, right? This is exactly what you would expect for a rank 1-1 tensor, right? That's the basis vector of a 1-1 tensor. And so right now it's looking like a 1-1 tensor. But I'm going to throw down another tensor product in here. And I'm going to call this next thing dx1 wedge dx2 wedge dx3. Right, so maybe I'll even put some parentheses in there. And then why don't I, just to be clever and show you how this all works out, I'm going to actually do it again. dx1 wedge dx2 wedge dx3. And this object, this is the object we're going to talk about right now. So in order to make a little bit of sense of what this is, let's break this down. Here we have the wedge product in the coordinate basis of a 3-form. Right? And here we have the exact same these two things are 3-forms. They're 3-forms with the coefficient of 1. Now, to understand the significance of the 3-form, we have to understand what is the dimensionality of the underlying vector space, right? We need to know what is dim v. And we're going to assert that dim v is actually 3. We're working in 3-dimensional space right now, which basically means that we're dealing, these two objects live in lambda 3 of v, and the 3 is maximal, right? So we know that the dimension of lambda 3 of v equals 1. Therefore, these guys here are one-dimensional, are members of a one-dimensional exterior power space because we're dealing with a dimensionality of 3. So just to be clear on this, this means we have there's a partial 1, a partial 2, and a partial 3 as vectors as a basis of v, and there's dx1, dx2, and dx3 that are basis vectors of the dual space. And the only basis vector of lambda 3v is the single basis vector dx1 wedge dx2 wedge dx3 in the strict coordinate, or the strict basis. And we're using that strict basis. So we've thrown that strict basis into here, and we've done a tensor product on them. And the tensor product applies here just fine because we do kind of remember that this wedge can be interpreted in terms of anti-symmetry over the tensor product, right? And once we understand that, in principle, we could make a replacement, and we could replace this, and we could replace this with something over a tensor product, in which case it would just be a long string of tensor products. Now, of course, this is a sum of tensor products, so this would be a linear, the replacement would be linear, right? And we would have, this guy would be expressed as a sum of different tensor products, but that's not a problem. Well, fortunately, we can collapse that sum by using this wedge. And regardless, these guys are elements of a one-dimensional vector space, and this is the only basis in that vector space. And so this tensor product here and here makes perfect sense. We are simply creating a tensor product using, so whatever this thing is, right, it represents an object where you take, you're creating a tensor product from the vector space V, tensor product from the dual space V, tensor product from the third exterior power space, tensor product from the third exterior power. That is a perfectly fine tensor product. It's completely okay. We always know that you can definitely tensor product V and its dual, but the truth is you can tensor product any sequence of vector spaces together, and they all operate in the same way as they ever would. In this case, the vector space has only one dimension, and in this case, it has only one dimension. And so that's what we've done here. That's the object we've created. So, let's think a little bit about such an object. For example, I'll come back to it. Let's do maybe a slightly simpler example. Maybe we just do an example where, well, no, this example is fine, but understand this 3 form, being one-dimensional, right? This is just the basis vector. You could imagine a component attached to this, right? This component here connects to these two. What about the components that connect to those two, right? This is a basis vector. These are basis vectors are summed on against the components. But remember, these things are one-dimensional. So we could, in fact, include their components in this thing. Let me imagine doing that for a moment. Maybe I can lower it. Let's imagine doing that. Let's imagine that we now have, we go K, fancy K, mu, nu, as the component of the first object, right, this thing. And this guy here is one-dimensional. So I'll say it's got just a component C. And this guy's one-dimensional. I'll call that component D, right? And then everything else is exactly the way it was before. dx nu, tensor product, and then dx1 wedge dx2 wedge dx3, tensor product dx1 wedge dx2 wedge dx3. So now I basically have the component of this part. This is the component for this basis vector, and this is the component for that basis vector. But these are one-dimensional, so there's no sum on these components, right? So there's nothing to stop me from just absorbing it into K mu nu. Maybe I call it K mu nu hat. So I haven't. So this structure here is really in full generality, even though this component looks like it's only being summed here. The only difference is a factor of C times D, because there's no sum over these two. In fact, I can take tensor products with these one-dimensional basis vectors from lambda 3 all day long. I can keep going and going and going and add, I could, without anything to slow me down, I could add another one. Wedge dx2, wedge dx3 if I wanted. And then all I would get is another component of that thing up front here. And then that again would be absorbed in there. So no matter how many factors, tensor factors of this I add, as long as I'm in the maximal dimension space where the maximal exterior power space where the dimension is 1, I will never change the structure of the component, right? I will have, it's not the same thing. I don't want you to mistake me by saying it's the same thing. It's not the same thing. This guy here with just 2 is different than this guy here with 3, right? If I get rid of this, I've changed it to one with 2 3 forms instead of one with 3 3 forms, and that's different. And the coefficient, indeed, will actually be different, right? Because this factor does come in. If I throw some vector down there, it has a component. It deserves to have a component in front here, just like this one deserved to have C, and this one deserved to have D. This one deserves to have E. The point I'm trying to make is that when I write down this object here in component form, all I need to do is express one thing that sums over the tensor parts that do not have one dimension. This guy, there's 3 of these, and there's 3 of these. So I need to sum over those 3. But there's no sum over this because there's only 1. So this is still the full generality, in full generality, this whole object. The way now I've written it as 3, with 3 3 forms. So the point I'm trying to make is that the rank of K, right? The rank of K does not change when we add one-dimensional objects to it, right? When we add one-dimensional objects to it, the rank won't change. So, and you can, and we've already sort of seen this happen, right? Because I can write V tensor product V star, say, and I can multiply by a constant, right? An element of C infinity of X, and then tensor product C infinity of X. These are just 2 functions, right? These guys they're one-dimensional vector spaces where the basis vector is the number 1, right? That's the basis vector. And I can multiply by functions all day long. And then this just ends up, those functions just end up with as regular factors on a vector. So I could write an element of this would be K alpha beta partial alpha tensor product partial beta tensor product the number 1 tensor product the number 1, right? And then I just put C in some function up front, say F and G, right? Where F is an element of that and G is an element of that. And now this guy, I just rewrite as K hat alpha beta partial alpha tensor product partial beta. Whoops, I guess this shouldn't be partial. This should be dx beta, right? And then this should be a dx beta like that. And sure, I can go tensor product the number 1, tensor product the number 1, and that just sort of becomes, it hangs on. Sure, it does hang on, but it doesn't add anything to it. It doesn't change the rank. The rank of this thing is still going to be 1, 1, right? Okay, so with that in mind, we now have created these interesting new objects where, although the rank is identical to a tensor of rank 1, 1, it's still not the same thing as a 1, 1 tensor because it does have these guys hanging on. So what are the implications of that? Well, of course, the implication is in the transformation, right? So let me rewrite that. K alpha prime beta prime, right? We're going to transform this thing now, right? Alpha prime beta prime. And so the first part of the transformation is, let's look at this thing here. This is what we're going to transform. We're going to transform this. So now what I'm going to do is I'm going to transform this guy and this guy, right? We're going to transform these 2 first. And what do we do? Well, the first one is obviously going to be, whoops, I'll do the transformations in red. I like that. See how that works. It'll be the inverse, or the contravariant matrix, alpha prime, alpha, and then the covariant matrix, beta, beta prime, times k alpha beta, right? So that's the transformation of the component, right? This guy right here. That's how that guy transforms. Now we look at transforming the basis vector, which is going to go the opposite way, because the transformation of this, the factor that transforms this, and the factor that transforms this has got to multiply to 1. So the next guy is going to be, let's see what it's going to look like. Lambda is going to have a alpha prime at the bottom, so it's going to be alpha prime, alpha, lambda alpha, like that. Where I'll keep the dummy indices this way by using these brackets, so the dummy indices are separated. In other words, these dummy indices are not the same as these dummy indices, right? So there's no confusion. And that will be tensor product with lambda inverse, and it will have to be, let's see, this would be dxb, so beta, beta prime, dx beta, like that. So ultimately, this is the transformation of the basis vector, this is the transformation of the tensor part, right? And that takes care of the transformation of this first part here, right? This first part here. So that guy we've got handled. Now, how do we transform this guy? And how do we transform this guy? Well, we just sort of remember our rule, right? That the transformation of if my linear transformation is a dx1 wedge, a dx2 wedge, a dx3, right? If I'm going to transfer each of the basis vectors of a wedge product of maximal dimension by a, I know that that equals the determinant of a times dx1 wedge, dx2 wedge, dx3, and that will equal dx1 prime wedge, dx2 prime wedge, dx3 prime, right? So I kind of remember that rule, that if I have the rule being that if I'm dealing in the space of dimension v equals 3, the maximal space, then if I transform each of the basis vectors by some matrix A, that's equivalent to taking the determinant of A out front, leaving those basis vectors behind, but this thing here is the definition of the transformed single strict basis element of the third exterior power in this case. So in order to transform this guy, right, in order to transform this thing into the prime basis, I need to multiply that whole thing by the determinant of the contravariant transformation matrix, because each of these is going to transform with the contravariant matrix because they're contravariant. So in this case, A is going to be lambda inverse. So I need to multiply this thing by the determinant of lambda inverse in order to transform it into the prime index. Same with this one, identically. I'm going to have to multiply it by the determinant of the inverse transformation matrix. So I'm going to need an inverse determinant to convert this and an inverse determinant to convert that. So I will do that. Let me get rid of this. And so now it's going to be the tensor product. All right, I got that. And it's going to be the determinant of lambda inverse times dx1 wedge dx2 wedge dx3, and I have that again, right? In fact, let's see if I can just use this thing to, I can actually create a second copy of it. Look at that. So this is identical, right? This is identical. We by multiplying by this inverse determinant, this is now the transformation of these things. The problem is I threw in these two inverse determinants, right? I threw in these two inverse determinants. Remember, everything has to be multiplied by 1. So in order to compensate for that, I have to multiply by the determinant of lambda twice, right? And that's because this times this is going to equal 1, and this times this is going to equal 1. So I know these guys are compensated for by these guys, but these two guys, in order to compensate for them, I need these two straight up determinants, which end up getting absorbed into the definition of the transformation of the components of this thing. That's the secret, right? So this ends up being equals the determinant of lambda squared, right, times lambda inverse alpha prime alpha lambda beta beta prime times k alpha beta. This guy I just rewrite as alpha prime tensor product dx beta prime. And then this guy and this guy I just rewrite in the prime basis. So it's going to be tensor product dx1, really? dx1 prime wedge dx2 prime wedge dx3 prime. Tensor product dx1 prime wedge dx2 prime wedge dx3 prime. And that is the transformation rule for this, well, for this object. Well, that is the transformation rule for this object here. This object in green, this guy here, its transformation rule, whatever this thing is, its transformation rule is, let's see, it's k alpha prime beta prime. The fancy well, let's see, well, this is the transformation rule, right? I guess the way we're peeling it apart here, this piece here is the transformation rule for the component KAB. So when I write KAB here, what I've kind of made some notational errors, right? Because this is clearly the components of something, just as this is the components of something. It's the components of this. These are the basis vectors of the total tensor product space that we're dealing with, right? And this is the components. It looks like a mismatch because there's more pieces of the tensor product than there are indices in the components, but I've already shown why that's the case. Dimension 1 things do not contribute to the rank. That's the key observation. So the transformation of this whole object is this process, or this whole process that we did here, throwing down the correct transformation matrices here, here, and here, or maybe I should, matrices here, matrix here, matrix here, and then throwing down these determinants here, here, and here to compensate. Now the component itself, that follows this law right here. I just peel off the basis vectors and I get the transformation law for the components. The transformation law for this basis vector here, right, multiplying by the determinant of the inverse, gives me the ability to just replace the unprimed with the prime coordinates. And the compensation shows up right there. So what we've basically shown is that I've created an object, I've created this object, but look what happened. The components of that object, that's this thing right here, transformed exactly according to the classical rules for a 1-1 tensor density of weight 2. That's what that is. It's a 1-1 tensor density of weight 2. And I showed how to build the real object. This is the part that you don't see. This is the part that you don't see in your classical treatment. You don't see this, right? You don't see this. And that, but that is consistent with our presentation. Our presentation, we always want to know, what is the basis vector? Because the basis vector really tells you what kind of tensor product space this thing lives in. And this tensor product space is not the same as, T11V. T11V does not have this stuff, right? That's different. Now, there is no standard notation out there for the tensor product space of a tensor density, but it is a vector space, because you add two densities together, you get another tensor density. There's an inverse tensor density for every tensor density, for an additive inverse. There's a zero tensor density of each appropriate weight. Now, how do we decide what weight it is? Well, the weight was simply the number of times we add these full-bodied forms, these maximal forms. Here was 1. If I had left this off, it would have been a tensor density of rank 1. Including it gives me a tensor density of, not rank 1, of weight 1. Including it gives me a tensor density of weight 2. If I had included this one, it would have been a tensor density of weight 3. Right? So I can always build these tensor densities by just adding factors, tensor product factors of elements from the one-dimensional maximal exterior power. In the strict basis, right? The whole point is in the strict basis. Now, if I had taken this and dissembled it into its tensor space basis, meaning if I had written it in the basis of the 0,3 tensor product space, right? Then this thing here would have become dx1 wedge dx2 wedge dx3. That would have become dx1 tensor product dx2 tensor product dx3 minus dx2 tensor product dx1 tensor product dx3 plus dx2 tensor product dx3 tensor product dx1, etc., 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 until all combinations, all permutations were accounted for. Then if I had taken this and substituted it up in here, then all of a sudden we have a full-blown tensor product, and we do in fact have components for each of these pieces. And those components, although they'll be totally anti-symmetric, those components will all transform according to the normal rules of normal tensors. What we'll discover is after we do all the transformations, we could still collapse everything back into this nice strict basis notation. So this is the unstrict basis, or the fully expanded basis. It's not even the unstrict basis. This is the fully expanded basis. I think the unstrict basis would be more like dx alpha wedge dx beta wedge dx gamma. And here you would have a alpha beta gamma with 1 over 3 factorial in the lead. You may remember that version of things, where you don't demand the strict sequencing of the indices. But if you do demand the strict basis, then that's what causes ultimately this tensor density thing to appear. Okay, so that is really what this whole story is about, tensor densities. That's the real nature of what a tensor density is. Now, that isn't the full answer for all the things you can do with tensors. but that is an important one. So maybe we can run through an example or two of some classically important tensor densities. Well, actually, no. I think I'll save the examples for we've already done an example, right? I mean, this is an example. This here is an example of a tensor density, right? We've done it. What I will do is we'll summarize, right? And well, what about tensor densities of negative weight, right? I could have k alpha beta partial alpha dx beta, and then I have a tensor product with an n vector, partial 1 wedge, partial 2 wedge, partial 3. Now the logic, and perhaps others, right? Now the logic is exactly the same. There's no difference in how this transforms, right? It still uses the inverse, the covariant, contravariant matrix, just like before, which multiplies up to 1. But this guy now, instead of a lambda inverse transforming each of these, it's going to be the covariant matrix. It's going to be lambda. So I have to multiply this guy by det lambda. And what does that do? Well, that forces me to multiply this one by det lambda inverse, right? But det lambda inverse equals 1 over det lambda. So this whole thing is just going to transform exactly the way this part is going to transform exactly the way a normal tensor would, but with an added factor of det lambda to the -1, right? So the weight becomes negative, right? And that's because now we're dealing with the n vector that lives in lambda 3v instead of the n form which lived in lambda 3v, right? So this is now that's how the weight negative weights appear, right? And of course, if you have no factors, then you end up with a 0 up here, right? You don't have to do it at all, and that is a normal tensor. So this is sort of the opposite thing. So you can create these tensors of positive or negative weight, integer weight, all day long by just adding, or by not adding, including factors of the maximal exterior power attached to the tensor. Now that's because we chose the dimensionality of v to equal 3, but of course it could be 10 or 20. As long as you end up drawing from 10, the maximal factor. If the dimension was 10, you have to draw from here, right? And that's because you need to use, where's that rule? Where's that rule? You need to use the rule that explains that, maybe I erased it, that the rule you need to use is that a dx1 wedge ... wedge dxn, the transformation a is equal to the determinant of a times dx1 wedge ... wedge dxn. If that's the that only works for the maximal space. For spaces less than the maximal space, this formula is slightly more complicated, and this guy ends up being a minor, right? A minor of the matrix, a minor of A. Okay, so we've created the real structure for the tensor densities. We're not talking yet about the applications of tensor densities, but they are key for the theory of integration on oriented manifolds. If you have oriented manifolds, oriented spacetimes, you can do integration using tensor densities. And the various things that are tensor densities are the Levi-Civita tensor, right? The so-called Levi-Civita symbol. I shouldn't say tensor, I should say the Levi-Civita symbol, E-I, J, K, etc. That thing is a tensor density. Also, the determinant of the metric is going to end up being a very important tensor density. We call that G. And G is the determinant of G mu nu. This thing here turns out to be it's going to be a rank. Let's see, rank -2, a rank 0 to tensor density of weight -2, right? And so we'll work with those, and eventually when we study the theory of integration on a manifold, which we're not going to do. All right, so this concludes the second part of our two-part series on the transformations of exterior powers. And it was an important part because it showed how the exterior power, the maximal exterior power, when added as a factor to a regular tensor, can actually produce this thing called a tensor density. And now, tensor density shouldn't be so mysterious, because anything's a mystery if you just arbitrarily create a definition like this. Oh, we're just going to slap on a determinant of lambda and call it a density. Well, it doesn't make any sense. But now I can show you, no, there is a actual vector space out there for which these objects here are the components. And this is it. We've actually constructed it. And we've shown that our understanding of the transformations of these things force us to have this determinant out in front. And we also understand this little weight thing too. Okay, so that's all for this lecture, and then the next lecture will, I'm not sure what we'll explore in the next lecture. I think we're going to start getting back into the notion of duality next time.